All right, lecture 26. This is the last lecture on Brayton cycles and gas turbines. I will go again over the efficiency increasing techniques for generation, reheat, and intercooling, but now we're going to combine them. And you will see that this leads to a particular kind of cycle that's called an Ericsson cycle if pushed to the extreme. And then we'll go quickly over aircraft propulsion, jet engines for aircraft propulsion, because these really are more jet engines and turbines for gas, for power generation. And then we'll come back to power generation and show you how combined cycles work, where you have a high-end, high-temperature cycle that's a gas turbine, and a low-temperature cycle that's a Rankine cycle. All right, so quick review of what we had last time. There are these regenerators. Regenerator cycles make use of the heat from the exhaust of the turbine to preheat the compressed air before putting it in the combustor, thereby taking enthalpy out of the exhaust stream, putting it back in the inlet stream, and saving the amount of fuel that you would otherwise need to add enthalpy to the system in the combustion chamber. So in the TS diagram, you go 2 to X through a heat exchanger, and then you add the heat from point X to point 3 through the combustor, thereby having to add less heat and improving your efficiency. The reheat cycle is one where you have topped your maximum temperature because, for example, of metallurgical limits to your turbine blades and your combustion chamber walls. And so since you can't add fuel to heat it to a higher temperature up away from 3, you just take a first stage of the turbine where you expand it first, 3 to A, and then you have a second reheat combustor where you heat it back up to point B, and a second stage in the turbine where you expand it again. And thereby you increase the total amount of work because you have increased the area under the curve, and you've done this without having exceeded temperature T3. The intercooler, on which we spent quite a bit of time last class, is one where you, in fact, do much the same thing that the reheat does to the turbine is what the intercooler does to the compressor. You take, so usually when you have a compression stage and it's an isentropic compressor, the temperature of the exhaust is higher than the temperature of the inlet. So if you go from 1 to pressure 2, you would have a fairly large temperature change. What you do is you take the air after the first stage of the turbine, you cool it back down to a temperature as close as possible to T1, and then you compress it again. And as I explained before, that decreases the amount of work you have to put in your compressor, the amount of work being the area of the PdV integral. So it's the area from B to 1 to 2 to A if it's an isentropic compression, or from B to 1 to C to D to 2 to A if it's a compressor with intercooler. So the intercooler essentially has saved you the hatched, dark blue hatched region of the work, and that, of course, means that you have a better efficiency in your compression stage. Now, a combined cycle uses all of the above. You can have two compressors with an intercooler in between, two-stage compression with an intercooler in between. After compressor 2, you use a reheat. You then go into use a regenerator. You then go into a first combustor. Then you use the reheat in a second combustor. Then you have a second turbine, and you go 9 to 10. So if you follow, you start from 1 to 2s, which is here. Then you come back through the intercooler to 3, which is here. Then you go to the second stage of the compressor from 3 to 4, which is here. From 4 to 5 is where you add the regenerator heat. From 5 to 6 is where you go through the first combustor. 6 to 7 is the first turbine stage. 7 to 8 is the second combustor. 8 to 9 is the second turbine stage. 9 to 1 is the exhaust that you've cycled. But going 9 to 1, you have first gone from 9 through the regenerator again to 10, which is an intermediate temperature on this isobaric cool down. All right. Well, so what you've seen is that in your TS diagram, you have essentially added little teeth here on the hot side, which enables you to design the whole cycle with the temperature below T6. So instead of going with a sharp tooth on the top, you have a set of small teeth. And what the intercoolers do is instead of going deep down to T1, you have a set of teeth, if you want, here in the TS diagram as well at the cold side. This is why reheats and intercoolers pretty much look the same on the TS diagram, except one is on the hot side and the other is on the cold side. So what they do is they try to make this temperature of the heat transfer on the hot side as stable as possible, because an isothermal heat transfer is the most efficient heat transfer. So one could push that to the limit. If I have a large number of reheats, my cycle in my TS diagram would look like this. And if I had a large number of intercoolers, my cycle on the TS diagram would have teeth here on the cold side as well. What you can see is that this makes this temperature more uniform. This makes that temperature, on average, more uniform. If I were to push this to the limit of an infinite amount of reheats, 3 to 4 would be an isotherm at T hot. And if I had an infinite amount of intercoolers, 1 to 2 would be an isotherm at T cold. And so it would reach this essentially unreachable ideal case where I'd have isothermal heat exchange both on the hot side and the cold side. That would be an Ericsson cycle, and it is more efficient. It looks more like a Carnot one. Now, it is not quite a Carnot one because these are isobaric, not isentropic, but you can't have everything. This is already good. Okay. Let's move to another section. These turbines, as we have seen them, mostly are highly optimized for efficiency, and they're mostly used, therefore, for power generation. If you were to look at propulsion, then the equation is entirely different. So what you really want in propulsion is a maximum amount of power in as lightweight, as small an engine as possible. And then, of course, you still want to have efficiency, but you want the efficiency without weight. Weight is a new added penalty. Weight and size are two new added penalties for aircraft propulsion. So the simplest form of a jet engine, and I'm now looking at an engine that's sort of World War II vintage, is to have your gas turbine consisting of the compressor stage between 1 and 2, the combustors between 2 and 3, and the turbine between 3 and 4. That part from between 1 and 4 is exactly what we had before. So it would look like 1 to 2 to 3 to 4. Now we do something with the incoming air, and we do something with the product air and the gases flare out. What we do with the gases out is that we want thrust. So thrust means we have to impart kinetic energy to the gases that come out of the turbine, and therefore we have to accelerate them essentially. And so what we do there is use an element from section 4, the nozzle. So the nozzle will create a change in enthalpy between point number 4 and point number 5, H4 minus H5, and transform that change in enthalpy into a change in kinetic energy, into a change in velocity. So per kilogram of mass flow, you have H4 minus H5 is going to be V4 square minus V5 square, the goal being to make V5 square as large as possible, because that is what's actually going to create thrust for your engine. So what you do is you have this nozzle with that equation. It cools the air from 4 to 5 in the nozzle, and here you have kinetic energy, V5 square, that's H4 minus H5. So this part, this cooling, this change in enthalpy that comes from this cooling, that is actually what gives you the thrust. Now, conversely, if you look outside the window of your aircraft and you look at the cowling around the engine, you will see that there is this rounded thing before the first compressor blades. The rounded thing is the diffuser. What it does is the airplane flies at a reasonable speed, 500 miles per hour or something, and so that air comes in, The kinetic energy of that air that comes in is not directly usable in the compressor. What you want to do with it is take the kinetic energy from the velocity of the air and transform it into an additional pressure or enthalpy, if you want, at point number 1. And so what you do at the entrance, what the cowling around the engine actually does, is it is a diffuser. The enthalpy change between point A and point 1 takes the velocity of the air at point A, which is in fact the same as the velocity of the aircraft, more or less, and it transforms that. So V1 is not that fast because you go through these blades. So you take this V sub A and you transform it into an additional enthalpy at point number 1, so that H sub 1 is the kinetic energy of the air in, plus H sub A, which is the enthalpy of the air outside to begin with. And so this then is used in the aircraft. H1 is closer to H2, so the overall work that you have to do with the compressor is smaller because you have used the ram air of the intake of the engine to increase the pressure. All right. Let me then represent an aircraft propulsion system in one of the diagrams that we like to have. So you look at your compressor, your combustor, your turbine that we had before for the gas turbine, and you add in front a diffuser, and you add in the back a nozzle, the nozzle being the thing that gives you thrust. And so that's how you calculate a propulsion system. In fact, we can make that as an exercise. Now one can push this a little bit further if one is interested in fun effects, and that is afterburners. So essentially fighter jets have engines that have an afterburner. So the afterburner is an add-on to this exhaust of the turbine. The beginning is the same. You have ram air in, so you transform the kinetic energy into enthalpy, you compress, you combust, you expand, and now you don't immediately transform this into velocity. What you can do is you can have a second array of fuel spraying bars, and you can then put a second flame here that increases the enthalpy just by heating. So what you basically do in the afterburner, is you add H4 minus H5, which is going to be here. H4 comes out of there. H5 is in here. That is simply going to be a second addition of heat, followed then by a nozzle, which transforms this additional enthalpy to kinetic energy. So that is what the afterburner does. You take this enthalpy here, you add enthalpy H5 to it, and then you transform the whole thing into kinetic energy, which is of course higher because you have transformed the heat into kinetic energy and therefore propulsion. Now one can push that a little faster. Why, in fact, do you need this gas turbine here if you could just use a diffuser to compress the air, add the flame, and then add the nozzle to expand the air without any moving parts? Of course that works. That's a ramjet. We'll get to that in 30 seconds because the book first goes you through the different forms of turboprop, turbofan, and ramjet. So in the turboprop, you have your gas engine, your gas turbine is here, the turbine here, the compressor is here. The work of the turbine in part is used to drive the compressor, and in another part is used to drive a propeller that's just in front of the airplane. So this is actually a simple propeller plane engine, but instead of having piston engines driving the propeller, you have a gas turbine driving the propeller. That's a turboprop. Most airplanes, most commercial airplanes that we fly in fact, are some version of a turboprop, except the cowling goes around the propeller. And that then becomes a high bypass turbofan engine. In a high bypass, it's exactly the same thing, except you have the cowling here and here, which is as if you had a propeller with a housing around it. And the fan, which is the equivalent of the propeller in front, then drives an additional bypass of air that goes through a bypass flow and then at the end, the bypass flow gets added to the air that comes out of the turbine. So this is in fact what most engines look like. And at that point, you can choose to look at the thrust of the engine, which is then the sum of the kinetic energy in the bypass air and in the turbine air, or you can choose to calculate the work that's put on the fan separately from the work that goes into the turbine, the compressor and the turbine drive both. And then the third form of propulsion is this ramjet, which is essentially an afterburner without a gas turbine in front. It's simply the diffuser, which increases the pressure using kinetic energy of the air that comes outside, and then the flame, and then the nozzle, which gives the kinetic energy back to the airflow. And that would work without any moving parts. Now, of course, it doesn't start, because if you don't have this air in, then you don't have this pressure increase, and then you have the equivalent of a gas turbine in which you would have a compression ratio of 1, and you know that doesn't go anywhere. So you have to have this diffuser compress the air that comes in, which you can only do if you have kinetic energy in the gas that comes in. And so here is a little review of aircraft performances as a function of specific impulse and Mach number, velocity. So most of the engines that are used for transportation have these turbofan engines here because the Mach number is below 1. And that is where you use the turbofan. You have fighter engines, of course, have a turbofan with afterburner. Now, once the speed goes above about, what, let's say Mach 3 here, you use this ramjet. So the ramjet is in fact the same as the scramjet. It's basically it's an afterburner here, and the compressor stage is made here simply by narrowing the shape of the duct, which increases the pressure on this side. So here you can transform your incoming velocity into a higher velocity, then you let it go. So here you have a high pressure front, and that's where you inject the fuel, and then you go through a nozzle, which transforms the enthalpy back into kinetic energy. This can all be done at very high Mach numbers with a different form, different shape of these things, and that's then supersonic flow. That is another elective later or graduate level class. These are very interesting to watch. I encourage you, if you have time, to take a little look at this little YouTube. And of course, it ends badly because at the end, they don't survive. But that's probably part of the fun. Let's say, now that we look back at power production and the most modern power plants that are gas-fired, used a combined cycle. So we combined chapter 9 and chapter 8. Remember, in the Rankine cycle, looked something like this. You had water as a circulating fluid between 7, 8, 9, 6, and 7. Your water went through a turbine, so this is now a vapor turbine, went through the condenser where you make water back up. The water is pumped back up to the high pressure in the pump, and then soon through a boiler or a steam generator. Go back to slideshow from the beginning and go back all the way back. Push the wrong button. Okay, so in a combined cycle, you exchange the boiler and the steam generator for, in fact, a heat exchanger that comes from a gas turbine. So you have a second cycle, a topping cycle this time, that takes in air, compresses from 1 to 2, combustion 2 to 3, 3 to 4, and it's the enthalpy in the air at between point number 4 and point number 5 that gets transferred to the water, where it gets transformed into an enthalpy that goes between 0.6 and 7 in the water. The advantage is that combustions take place in the gas phase. The gas temperatures in a combustion is maybe 2000 Kelvin. Well, you know that you can use your turbine entrance around 1500 Kelvin. So the temperature difference between the combustion process itself and the turbine is, let's say, 500 Kelvin or so. It's much less than it would be if you use the combustion process directly to heat water, because this point here is at 500 or so degrees centigrade, 700 Kelvin. So you're better off using your gases, which are 2000 Kelvin, to heat a 1500 Kelvin point than to heat a 700 or 800 Kelvin point. That's why this is then the topping cycle. And of course, when you have a topping cycle that has, I don't know, 20% efficiency and a bottoming cycle at 30, you end up roughly with a combined cycle that has a very nice efficiency, reaching or exceeding a little bit 50%. Now, one catch, of course, is that you're going to be burning in your combustor only natural gas. If you try to burn coal here, of course, the coal dust will just ruin your turbine. Nobody designs for that. And that's it for gas turbines. Thank you.